Hello there. Today I'm going to talk about a very basic voltage regulator, the one that you see here in this circuit. I remember I built this voltage regulator for a 50 watts audio amplifier. That's of course for the preamplifier that voltage regulator was, and it wasn't for 100 milliamps output. I remember it was for a 500 milliamps output. Okay. Anyway, this basic regulator has very nice ideas hidden in it. Okay. Now the input voltage for this voltage regulator is between 12 volts and 25 volts. Regulated voltage, of course. Not regulated, but smoothed. That's a better word to say. And the output is a plus 10 volts regulated voltage. The current, as shown in here, is 0 to 100 milliamps. That's the output current. And of course, it can be increased to 500 or even 1 amp, 500 milliamps, or even 1000 milliamps by changing few components, by calculating the values of these components. Now, what this voltage regulator is made of, it's made of a pass transistor to pass the output current. It's made of a voltage divider between the output and the ground, made by R2 and R3. It's made of this, let's say it's the control element, or an NPN, small NPN transistors. It's a very basic type and very low cost. It has the reference voltage, which is made by this zener, 4.3 volt zener. Okay. And that resistor that's connected between the input voltage and the base of the pass transistor. Now, how this circuit is supposed to work? By the way, before we go further with our lecture, let me say that what I'm using in here is the electronic current, where the current passes from a low potential to higher potential. This is how the electronic current works. Electrons move from the negatively charged pole to the positively charged pole, or goes toward the positive element. Okay. Now, how does it work? How does the circuit work? You have a voltage divider in here. Okay. And you choose that voltage divider to suit the requirements that you have. For this case, you have a 10 volts in here, and those two resistors are equal, and they are choosing equal because the reference voltage for the circuit is made of 5 volts, which is the zener voltage, the 4.3 volts by the zener. Add to it the VBE, which is around 0.7, so that means that makes the reference voltage to be 5 volts. And since both of these resistors are equal, so you will have 10 volts in here, because the same current, we assume that the same current that passes through this resistor equals the same current for this resistor. Of course, if you want to talk accurately about that, no, the current that passes through R2 has to pass IB of this Q3, or that control element transistor. So you have an IB passes in addition to the current of R3 through R2. So we have two current passing through this resistor. You have a single current passing through this resistor here. Okay, now how does the circuit work, or what you should calculate when you design such a circuit? Now to choose this resistor in here, which is R1, that depends on the HFE for that pass transistor that you have in here. That 3055, you have about 5 versions of it. You choose the one which has a high HFE or a high beta. There are a few types are available, because that will make it easier for the control element or the control transistor to pass the IC required for it, and that allows smaller resistor to be chosen in here. Anyway, when you want to choose this resistor in here, you take the minimum voltage in here, which is about 12 volts. And we know that the voltage in here is 10 volts. So VB, this Q1 will be about 10.7 volts. So list with about 1.3 volts. Those 1.3 volts, okay, divided by the minimum HFE of this transistor will give you the value of this resistor. And as we see in here, it's going to be a small value. This is the lowest value of R1 that you can choose, is having the 1.3 volts across it, okay, and it has, under these conditions, to pass the IP required for this transistor to provide the 10 volts in here, which is, to be safe, is the minimum HFE for this pass transistor. Okay, you guarantee now that you can supply the 10 volts at that output under these conditions. So this is the minimum value for R1. Now, since you chose R1, and as we said before, since we need 10 volts to be in here, this resistor will be equal to this resistor. Okay. And we have to choose the value for these resistors to make sure that you have a stiff network in here. The current that passes through R2, R3 and R2 must be at least 10 times the current expected from IB. So IB in this case can be neglected. When you have a stiff network with a current that passing through these two resistors is 10 times the current that will pass through IB of this transistor. Okay. And so since we chose the reference voltage to be 5 volts in here, that allows us to calculate these two resistors, and we're going to see the equations later on. And these equations are almost standard for all types, for many types, let's say, of power supplies. Okay, things to take into consideration, that whenever you have the maximum input voltage to be 25, for an example, as said in here, you have to make sure that when this voltage is available, and knowing what kind of current will be passing through this resistor, you have to make sure that that transistor can supply that current. So the maximum IC actually will depend on the maximum input voltage that you have in here. Okay, you take it around 10.7 volts, so you're left with about 14 volts. Those 14 volts, when you divide them by R1, which is what he said, you have to choose the minimum one if you're going to operate between those two ranges. You divided those 14 by the chosen value for R1, that will give you the maximum IC that you're going to have, that you're going to see around here. Okay, because the duty of the circuit is to keep this 10, to keep this 10.7, okay, and when you have a 25 in here, that means you left with about 14.3 volts across this resistor, and those 14.3 volts has to come through the current that passing IC, that passing through this control element through R1. So this is the one that had to supply the current. I don't know if we can just talk a little bit about the currents. The arrows shows the currents that you have in here. You have the return current going through this zener, okay, through the anode of it, of course, and after that through the emitter. And the emitter current splits into two, IP in here, and IC in here. Okay. Now IB is joined with IR3 to go through R2, the one in here. Okay. And that, of course, along with the current from the load, will go through the emitter of the pass transistor. And the emitter of the transistor will have its own IB and its own IC. And IB of it will go this way and join together with what? With IC that we have from the control element. So what you have through R1 is IB of the pass transistor. Add to that the IB of the IC, of the control element, IC of the control element. And that all go toward the most positive point in the circuit, which is the input or the supply. Now, how does the circuit operate exactly? And this is the main idea that I want to talk about. It's not the idea that you can control, that you can calculate the currents going through these devices. Actually, it does not work that way, because when you have in here a 10.3 or a 10.5 or whatever, you want to know exactly what's happening in this circuit and how you can actually have those 10 volts in there and to be regulated. Okay. And the idea in here that you have that VPE added to the VZ. And the idea in here is not what currents are going in or out to control the circuit, but a different thing. It's not actually something that depends on the HFE of that Q2. That's not the main thing that you calculate your components around it. What happens in here is you have to look differently at these two components, that Q2 and that VZ. And we apply in this case the ABERS-MOLL equation, and I'll just discuss it a little bit now. The ABERS-MOLL equation, which simply states that IC of this transistor is controlled by the VBE of this transistor, not by IB. This is the main thing I want to talk about. Okay. So IC of this transistor, which of course controls the pass transistor, actually dependent on the VBE of this transistor. Okay. And how is that? Let me just show you another graph for this transistor and discuss it just a little bit. We have this photo in here, as you see. First of all, as we see in here, the HFE for any transistor, it starts increasing as IC increases, and after that it settles. Okay, and this is, I believe, the typical value. They calculate for the typical value in here. Unless it's given an IC or an exact IC, an HFE for an exact IC. or it levels in here. So in here it increases, it levels, and it starts decreasing. Okay, this is HFE. That's why you cannot calculate accurate circuits using the HFE, because it keeps changing, or it changes. Okay. This is the equation in here. It's here in here, the ABERS-MOLL model. This is the model applied for the basic transistor circuits. This is the ABERS-MOLL. And this is the main, this is the figure that shows much of what I'm talking about, which is the idea is that VBE is what controlling IC, not IB. Okay, and note in here how linear it is, how linearly IC is changing with a changing VBE. Okay, while if you want to work with HFE, you're going to see these fragmented slopes where HFE starts increasing at a low value of IC, and after that becomes linear, or let's say steady state, steady or stable for this part, which is up in the top somewhere. And if you keep increasing IB, you're going to have a lower HFE. HFE starts decreasing with an increasing IC or IB. Okay, so it starts decreasing. So it increases, becomes stable, then it starts decreasing with an increasing IB. While in here you can see that IC is stable exactly with the VBE. Okay. And to know exactly, or to know more information about that, is that you'll find out that according to this equation, or according to the figure that you have in here, okay, that a 60 millivolts change of a VBE will increase the current by 10 volts, or an 18 millivolts change of VBE will double IC. Okay, and this is all in this equation here. And what this equation states actually is VBE equals KT over Q, the natural logarithm of IC of IS. Now VBE, we know what it is. K, it's the Boltzmann constant. T is the temperature in Kelvin, which is around 300 degrees at room temperature. A Q is the charge of an electron. Okay, the natural logarithm, IC, which is the IC of the transistor, over IS. This is a number given by each manufacturer. It has to do with how the transistor is designed. We don't really care much about it. Sometimes they call it a saturation current, but it has to do with each particular transistor. Each transistor has its own IS. Okay, but the main idea is to know that when VBE, whatever it is, it's 0.5 volts or 0.6 or whatever, when you add to it 18 millivolts, additional 18 millivolts, multiplied by KT over Q, which is around 25 millivolts or 26 millivolts, okay, that will give you double of IC. Whatever IC was, it was milliamp, it will become 2. It was 2 milliamps, becomes 4. And if you added 60 millivolts to VBE, you're going to have 10 times IC. You can plug these numbers and play with them to see how these things works. So the idea that you're controlling IC with the VBE. Actually, whenever you want to work with differential amplifiers or circuits that calculate the root square or let's say the powers or any differential amplifiers, whatever, you have to work with something like this, with the ABERS-MOLL model, because it gives you exactly what's happening, or transistor mirrors, whatever. So this is the idea. Okay, now go back to our circuit again. So as we see in here, if you have, let's say, you won't need it actually, if you have, let's say, about, let's say, 36 millivolts additional to those 10 volts. 36, they won't be seen actually. They won't be measured when you have a 10 volts in here. 36 millivolts, and that means you got 18 millivolts at this voltage divider, because this resistor is equal to that resistor. And an 18 millivolts in here will double the current of this transistor. That means it will double it. So whatever voltage you got in here, it will double. So you see, either you won't reach that. If you double it, that means if you are operating at 25 volts in here, doubling the current means you're going to need about 50 volts to sink the whole current in here. That tells you that you won't need as much as that, okay? In here, just a few millivolts in here, just a few millivolts will be enough to control, to make a huge current change in here that will affect this resistor and immediately, okay, to lower the value of this IB. Now, how does the feedback works? Just to give a slight idea about it, okay? A slight increase in voltage in here. Half of that, a slight increase will appear in here. This transistor, as we said, 18 millivolts will double its current. When that current increases, it will pass through this resistor. That means it will develop more voltage across it. That means it will push this base down with more voltage across it. When you push this down, VE of the base transistor will also go down, and that will reduce the output voltage. Okay, and the same thing, if you reduce that voltage farther than the 10 volts, that means this will decrease. Half of it will be here decrease. And this transistor, when the voltage across it decrease, will decrease the IC through it. Okay, that means the voltage across this resistor will also decrease. Okay, which means you're going to pull it up, and you're going to pull VE up with it. So this is how the feedback mechanism that works in here. Okay, now let's see the equations. They are very basic equations, by the way. And the idea that you're going to see, what they call, they're going to see this equation frequently, because you always have that feedback network, and you got always that V reference in here. And this applies to many other circuits. I don't know, I might be able to put more lectures on voltage regulators. You're going to see this frequently. And the V out will equals to V reference, okay, multiplied by the multiplier of the feedback. Okay, what is the V reference that we have in here? It's nothing but the VZ, okay, and add to it the VBE, and that equals to 5 volts. And the multiplier is nothing but this resistor in here, R2, added to R3, divided by R2 again. Okay, that's the multiplier that we have in here. And when you take R2 out of the equations here, you're going to be left with 1 plus R2 over R3. Okay, because R3 is repeated twice. The idea that the same current passing through both of these resistors. And we're going to see this down here. So the output voltage will finally be equal to 5 volts over the parenthesis 1 plus R2 over R3, or 1K over K. That means you have 2 in here, 2 multiplied by the 5, you got your 10 volts in here. And how this goes, you have R3 equals to R2, almost, except that R2 will have another IB through it, so we neglect it because it's about 1/10 of the voltage with the current that passes through R3. And the voltage, of course, V out will be equal always to V R2 plus VR3, and the same current like we said passing through them. And what is the voltage across R3 is nothing but the 5 volts. That's the voltage in here. It's always VR3 equal 5 volts. VR2, it has the same current, so you're going to have VR3 over R3, okay, multiplied by R2. So this is the current of R3, which goes through R2. So multiply the current by by R2, you give voltage of R2. And again, the same thing repeats itself. V out will be equal to the 5 volts, which is exactly the VR2 in here, the 5 volts, same thing, plus the 5 volts sorry. You have your own 5 volts, which is exactly the voltage of R2. And you have the voltage left with the voltage of R3, which is nothing but the current that passing through R2 multiplied by R2, which is 5 volts over R3 multiplied by R2, okay, which equals the same as we said before, 5, open the parenthesis, 1 plus R2 over R3. So the circuit is very, very, very basic, but it has good ideas. I love to share it with you. That's all. Hope you like the video, and thanks for watching.